What's up, Funky Bunch? Mr. A here with another amazing video for you. Today, what we're going to do is just have a couple of sample problems for limiting reactant type problems. All right, hopefully we can get through these pretty fast and we have some fun along the way. Without further ado, let's get started. All right, so in this question it says, suppose 25 kilograms of nitrogen gas and 5 kilograms of hydrogen gas are mixed to form ammonia. Calculate the mass of ammonia produced when this reaction is run to completion. Alrighty. Now, first thing we should do for this particular question is, well, write a chemical equation describing this reaction. Now, maybe you don't remember, hopefully you do. When we see certain gases like nitrogen gas and hydrogen gas, we should remember those are diatomic, meaning it is N2 plus H2. And remembering that ammonia is NH3. So now that we wrote this equation, next step is going to be to balance it. And I'm just going to go ahead and balance this puppy out here. Nice. Real nice. Now we have a balanced equation. Now we can get to the fun stuff. All right, so we know we are given two reactants, the amounts of two reactants. We have 25.0. Actually, let's do this. They actually give us the gram value, which is what we're going to use because we can convert between grams and moles. I mean, with kilograms, it means not really that much different. A little bit multiplication, but this works just fine. So I'm going to expand those as well. I'm not going to leave them in scientific notation just because it'll be easier for us. So 2.50 times 10 to the 4th. So 1, 2, 3, 4 grams of nitrogen gas. That's a lot. Wow. And 50,000 grams of hydrogen gas. Okay, so that's what we're given. Now we're trying to find the mass of ammonia produced. And then it says this thing here, reaction is run to completion. So what that means is that we're going to run through this reaction until we run out of one of our reactants. Right, so what we have to do in order to solve the main problem, right, our main question, which is what's the mass of ammonia produced, we have to figure out what's going to limit us, what reactant is going to limit us in our production of ammonia. So in order to do that, we learned two methods to do that from the previous video. I'm going to be using approach 2. Okay, so in approach 2, with both of these amounts, we're going to try to figure out how many grams of ammonia can be made by each one of these reactants. Okay, so in this first line here, N2, what we're going to do is assume we have enough hydrogen gas and that we're going to use up all of the nitrogen gas. So that's going to be our driving force in this calculation. So first thing I'm going to want to do is divide this mass value of, by its molar mass. So we know that the molar mass of nitrogen is 14.01. However, it's N2, so we need to make sure we multiply by 2 and not delete any of our Fantastic work. So we get 28.02 grams per mole, which will cancel out our units of grams. So now we're in moles of N2. All right, wonderful. Now that we're in moles of N2, we can convert to moles of NH3 by using a mole ratio. Looking at the coefficients, you can see that there's 2 moles of NH3 for 1 mole N2. And now we can cancel out units of nitrogen gas. We're left in moles of ammonia, almost to our answer. The last step is going to be converting this mole value into grams. So what we need to do is find the molar mass of ammonia and multiply that to this mole value. So ammonia has a molar mass of, I was going to put 17, let's do 17.03 grams per mole. This will cancel out moles. Now we're left in grams. Wonderful. So doing the math, we got 25,000 times 2 times 17.303 divided by 28.02. Let's go ahead and plug that into the good old calculator machine. And with some very, very hard computing skills here, I can figure out that our answer is 30,400 grams of ammonia. I'm going to write the actual answer right here, 3389, just in case there's some things we have to consider with our sig figs. I'm hoping it doesn't come to this. You know, for so long, I keep pushing the limits of science. And eventually it's going to catch up to me. I hope today's not that day. Stay tuned to find out. Anyways, now that we know that 25,000 grams of nitrogen gas can make 30,400 grams of ammonia, we're going to have to figure out how much ammonia can be made from our hydrogen gas. Whichever one produces the least amount of ammonia is going to be our limiting reactant. So let's find out which one that is. Now, following the same general steps as before, only thing is now we're dealing with hydrogen gas. So dividing by its molar mass, hydrogen gas's molar mass is 2.016 grams. There we go. Now converting from moles H2 to moles NH3, 2 moles ammonia for 3 moles H2, and then multiplying by that molar mass of ammonia, which we found before. Our units here cancel, left in grams of ammonia. Perfect. So doing our math, 50,000 times 2 times 17.03 divided by 2.016 divided by 3. And going to the 5th dimension to pull these numbers straight from the air, if I can actually type this in properly. What? Is that even possible? Such things are possible. Indeed. Indeed, young Padawan. And we can find out this makes roughly 280,000 grams of ammonia. So let's just review what we found here. In writing, if we use all of our nitrogen gas, we can produce 30,400 grams of ammonia. If we use, so these little quotes here just mean copy down, 50,000 grams of hydrogen gas, we can produce 280,000 grams of ammonia. You know, I'm not a math wizard or a math magician, but I'm pretty sure this is a lot less than 280,000. So, what did we just find out? We found out two things. We found out that nitrogen gas is our limiting reactant. We know that because it can make the least amount of ammonia gas, right? So if we used up all of this hydrogen gas, we could have made this much ammonia. But since we only have this much nitrogen gas, we can only make this much ammonia. So nitrogen gas is our limiting reactant. And answering our question, the mass of ammonia produced, well, that's going to be 30,400 grams of ammonia. Think about all the things you can do with that ammonia. And that was the time to think about what you could do with ammonia with Mr. A. Alrighty, hope that was fun, because it was fun for me. Let's move on to one more example. Putting the lime in the coconut, shaking it all up, we can see a limiting reactant problem up here. We see that, well, we have a nice reaction going on here, and it says what mass of water is required to react exactly with 249 grams of methane. That is how much water will just use up all of the 249 grams of methane, leaving no methane or water remaining. That's high quality stuff there. Left me on the edge of my seat personally. So let's get to it. Now, well, actually, let me see this. What this question is asking, or what it's telling us, is that we have in our possession 249 grams of good old-fashioned methane. We want to know if we use all of this up, how much grams, right? Yeah. Oh, this says how much water. We'll do grams because let's just do it. Why not? Let's just go for it. How many grams of water do we need to react with this many grams of methane? Okay. So, what we're going to do is this problem right here. Now, this is not really a limiting reactants problem. This is more so one of our mass mole problems. So I'm just realizing that now. So I'll make another problem up after this. and everything will be fine. Okay, everything will be fine. It's gonna be all right. I promise. So let's just crack through this one real quick and get to the better stuff. Okay. So we know our start point. We know our end point. Let's just get along to it. Grams to moles of methane. We need to divide by the molar mass. For this, it's going to be, what is that? 15, nope, 16 grams per mole. Just doing some rounding, so this is a little bit faster. Getting a mole fraction, nope, mole ratio. We're going to have 1-to-1 ratio, huh? Yep. 1 mole H2O, 1 mole CH4. And lastly, we need to multiply by its molar mass. H2O's molar mass is 18 grams per mole. Looking at the units, these grams cancel out. These moles cancel out. And these moles cancel out. We're left in grams of H2O. Perfect. So now we just do 249 divided by 16 times 18. This is pretty close to the same thing. 280 grams of H2O are needed to react with 249 grams of methane. All right, so that's what happens when you don't plan properly. I just assumed because it said limiting reactant on there that this was going to be a limiting reactant problem. Little did I know, I can't even trust myself nowadays. So maybe that's a good lesson. Trust nobody, not even yourself. So when you look in the mirror, I just want you to know that I'm talking to the man in the mirror, and I am asking him to change his ways. That no message could be any clearer. That's all I got. I mean, what else do you want from me? Come on. Come on. So, just getting a little bit back on track here. Let's come up with a problem for us. One last problem that is actually a limiting reactant problem. And then we can all just kumbaya, relax, and enjoy the knowledge that we feasted on in this video. So let's say we have a reaction of zinc sulfide with oxygen gas forming zinc oxide and sulfur dioxide. Man, I don't even know if I could balance this thing. This was not a good idea. Oh boy. Oh jeez. Why did I choose this? What am I doing? That's gonna be okay. It's gonna be okay. Well, let's see here. I'm gonna put a 2 here temporarily because why not? And then I'm gonna throw a 2 in here, which means I need to put a 2 in here, which means I'm gonna need 2, 4, 6, 3 right there, and I think we did it. I think so. I'm gonna make those different color because I can. 2, 3, 2, 2. That's pretty weird. That's the code to the safe holding the Declaration of Independence. Not that I would know those kinds of things, and not that I'm friends with Nick Cage or anything. Let's get a problem here. So let's say that we have this reaction. If 1.72 moles of zinc sulfide react with 3.04 moles of O2. How much sulfur dioxide in grams can be produced? And we ain't talking about lettuce. Now, so we're given our two reactant amounts, right? Zinc sulfide, oxygen gas. We're trying to figure out how much of this product, SO2, we can make, right? So what we need to do again is figure out first, what's our limiting reactant? And second, what are how much product can be made actually, which is dependent on that limiting reactant. Alrighty. So what I'm going to do in this problem is use approach 1 from our first video on limiting reactants, which is more of a step-by-step process, first finding what the limiting reactant is, and then finding the amount of product made. All right, so let me just put, we're using approach 1 here. I don't think I did this for the other one, but oh well. So let's get to it. What we're going to do, let's write down our starting points here. We know how much of each of our reactants we have. And what we're going to do is make two equations here, two lines of calculations. And in this first one, what we're going to do is say if we use up all of our zinc sulfide, how many moles of oxygen do we need to do that? So all we need to do is use a mole ratio to convert from moles of zinc sulfide to moles of O2. So looking at the coefficients, 3 moles O2 for every 2 moles zinc sulfide. And we find out that we have, or we need rather, 2.58 moles of O2. Now down here, we're going to do the same thing, but if we use up all of our O2, how many moles of zinc sulfide do we need? So the ratio there would just be flipped. 2 moles zinc sulfide for 3 moles O2. Let me put those crossouts there. And we get 3.04 times 2 divided by 3, 2.03 moles of zinc sulfide. Now what we do is compare what we need versus what we have. So over on this left side, this is what we have. Have H-A-V-E. This is what we have. This is what we would need. And we're not talking dough. Unless you're talking about all that dough I'm making. Ha! Just kidding. Anyways, comparing, we would need 2.58 moles of O2. We have 3.04. So we have enough. Wonderful. If we used up all of our O2, we would need 2.03 moles of zinc sulfide. We have 1.72. And unfortunately, we don't got that. We don't got that. So what we determined there What's this doing here? What is this? Anyways, what we have here, what we have found is that zinc sulfide. So 1.72 moles of zinc sulfide is our limiting reactant. All right. So now that we found that that's our limiting reactant, zinc sulfide, we can use that to calculate or find out the amount of sulfur dioxide we can produce. Okay, so we're going to use this as our starting point for our calculations. We know we want to get to grams of sulfur dioxide. So since we're already in moles, we can just use a mole ratio to convert from moles of zinc sulfide to moles of sulfur dioxide. And it looks like that's a 2-to-2 ratio. Okay, wonderful. Now that we have our moles of sulfur dioxide, we can go ahead and multiply by the molar mass of sulfur dioxide, which is 64.1 grams per mole. This will put us into units of grams of sulfur dioxide, which is quite frankly what we wanted. It's what you've wanted all this time. You didn't even know it. So, well, I mean, actually, I hope you did know that. So, that would be awkward. Anyways, let's do the math. 1.72 times 64.1. We get that. We can make 110 wonderful grams of sulfur dioxide. Wow, that is fantastico. All right, so again, what we did in this first set of calculations, we determined that zinc sulfide is our limiting reactant. Once we determine that this is our limiting reactant, we use that to calculate how many grams of sulfur dioxide we could make. And with that, this video is in the books. It's been quite the adventure. We had some highs, we had some lows, we had some of those parts where it's really just in the middle, hey, we're okay. Hope you enjoyed. I hope this was fun. As always, learning should be fun. If you're not having fun, are you really living? Well, I mean, I guess you don't necessarily have to have fun to live, but you get the point. Once again, I am the amazing Mr. A. Hope you enjoyed the video. Make sure you like, subscribe, and hit that wonderful bell. Pretty soon I'm going to become a professional bell drawer. I don't know what that thing on the top's supposed to be, but imagine we had a hook. Hey, there we go. Why not?